Unlike strong acids, weak acids, as have been alluded to before, do not ionize completely in water to produce hydrogen ions. They exist primarily as molecules. Examples of these are carbonic acid in carbonated beverages, ethanoic acid in vinegar, ascorbic acid in vitamin C, and acetyl salicylic acid in aspirin. Ionization of weak acids. The ionization of ethanoic acid will be used to represent how weak acids ionize in water. So this equation shows how molecules of ethanoic acid ionize to give ethanoate ions and hydrogen ions. This table provides some information about how ethanoic acid ionizes in water. I want to take this opportunity to talk about strong acids and weak acids, and about strong bases and weak bases. But before I do that, I just want to repeat this demonstration here by inserting these electrodes into acetic acid, or ethanoic acid, or vinegar, and observe the intensity with the light bulb lights up. Okay? Now I'm going to put it into hydrochloric acid and see the difference. Who can say why the bulb lit up dimly here and very brightly there? Okay, go back to our understanding of why these things that are called electrolytes. By the way, those salt solutions and these acid-base solutions here, all called electrolytes. Why does the electrolyte conduct electricity? Because of the ions that are present inside. So the more ions something has, the greater will be the degree of conductivity, as in the case of hydrochloric acid, compared with ethanoic acid. So what can we say about the concentration of ions in hydrochloric acid compared to ethanoic acid? We can simply say that this has a higher concentration of ions than this one. That is why it is able to conduct electricity much more than this one. So why is that? The explanation for that is this. It is said that hydrochloric acid is a strong acid. So a strong acid, therefore, is said to ionize completely. These are molecules of hydrochloric acid. You can see they're molecules, right? Before they dissolve in water, they are molecules. But when we dissolve the acid in water, this is what happens. They ionize, okay? Hydrogen and chlorine ions separate from each other, right? The hydrogen separate away from there, okay? You can watch that, okay? Here, they're breaking apart, they ionize like that. It is said that for acids such as hydrochloric acid, there is 100% ionization. And because of that, that is why we have this high conductivity. So an acid that is said to be strong is one that ionizes completely. And of course, if it ionizes completely, it will have a high concentration of hydrogen ions, which causes acidity. Unlike that, the ethanoic acid wasn't able to ionize completely, and we call such an acid a weak acid. For example, if I had these molecules here, right? These are the molecules before they dissolve in water. So what happens when they dissolve in water, most of them will remain as molecules, but only a few of them will ionize to produce hydrogen ions and ethanoate ions. That is why there are few ions there to conduct electricity. And as such, we say such acids are weak acids, okay? So these are some figures here that I want to show you here, right? Look, if I had 1,000 molecules of hydrogen chloride, it's called hydrogen chloride before it ionizes, okay? If you had that and I have zero number of chloride and hydrogen ion initially, right? But the moment you dissolve that in water, look what happens. That's initial. Finally, you'll have zero number of molecules there, but all will be in the form of ions. So this is 100% ionized. That's why when we show it for a strong acid, you put an arrow going like that. In case of acetic acid or vinegar, if we start up with 1,000 molecules, you'll have 0 and 0. Finally, look what happens. all of these will remain unionized, but only 13 ions of hydrogen and 13 acetate ion you're going to have there. That is said to be a weak acid. Same thing holds for bases, right? In this case, you're going to say ammonium hydroxide is a weak base. You can do that again. This is ammonium hydroxide. See that? Lit up dimly. Okay? Sodium hydroxide, very bright. This is sodium hydroxide is said to be the strong base, and ammonium hydroxide will be said to be a weak base. Okay, so the strong base and the strong acid ionize completely, 100% ionization. The weak base and a weak acid only undergo partial ionization, and you'll see that. If you want to talk about sodium hydroxide now, you put AQ, you're going to put a one single arrow here to indicate that there is 100% ionization. Okay? All right. Well, I hope that was able to let you understand the difference between strong acids and weak acids and strong bases and weak bases. Thank you. Of course, this is the equation that represents its ionization. Every molecule of ethanoic acid that ionizes produces one ethanoic ion and one ion of hydrogen. According to this table provided, if 1,000 molecules of ethanoic acid are present, initially we do not have any ethanoic nor hydrogen ions present. However, the final analysis of the equilibrium mixture shows that 987 molecules of the acid remain unionized, and only 13 of the 1,000 ionized to give these number of ions, 13 and 13 here. It can thus be said that ethanoic acid only partially ionizes, since the bulk of it remains as molecules and only a few ions are present. We'll now try to show how the percentage ionization of weak acids are calculated. Based on the information provided here, it wouldn't be difficult to calculate the percentage ionization of this acid. We started with 1,000 molecules, but only 13 of them ionized to produce these ions. To find the percentage ionization, we'll take either of these, you're more interested in hydrogen ions, and put it over the initial concentration and multiply that by 100%. So percentage ionization will be equal to 13 divided by 1,000 times 100%. In this case, the 13 can be representative of either the ethanoic ions or the hydrogen ions. We use hydrogen ions because we're more interested in that, as you'll see later on. And these 1,000 molecules here can be representative of the initial concentration of the acid. But like we said, we are more interested in the concentration of the hydrogen ions. So we'll rearrange this equation to make hydrogen the subject of it. So rearrange in all of that, this is what H plus becomes, is equal to P times the initial concentration of the acid divided by 100%. Now we'll learn how to calculate the hydrogen ions concentration and the pH of weak acids. We solve this problem to show how that is done. So solve the problem number 1. You're given this concentration of methanoic acid that has that formula, and we are told that it is 4.2% ionized. And we want to use this information to calculate the hydrogen ion concentration of the solution. Okay, so now we have two things that are provided. We are given the concentration and we are given the percentage ionization. We know this, we know that, and we know percentage ionization. And this is also given. Putting all those values into this equation, the hydrogen ion concentration turns out to be 4.2 times 10 to the negative 3 moles per liter. You can now be further asked to calculate the pH of the solution. And we know that pH will be negative log of hydrogen ion concentration. We've just found the hydrogen ion concentration to be that, though negative log of that, and the pH turns out to be 2.38. So that's pretty easy. You're given the concentration, you're given the percentage ionization. You know three things. The only thing that's not known is this, and it turns out to be this.
then you can ask to find the pH of that, do a negative log of it, and that's where you get the. Now we asked to calculate the percentage ionization of weak acids. We'll solve another problem to show how that is done. We'll read that and then we'll show how it is solved. We're told that the pH of a 0.1 mole per liter solution of ethanoic acid is 2.89, and you're asked to calculate its percentage ionization. So this is the general formula we had before, that P over 100% is equal to H plus over H8. You want to find this guy. This is given, but we do not know what H plus is. But we know what pH is. Go back to your grade 11 chemistry, where we're told that if you're given the pH, you can find the hydrogen ion concentration by taking 10 and raise it to the negative pH value. So the H plus concentration will be equal to 10 raised to the exponent, negative 2.89, and it turns out to be that for the concentration of hydrogen. All you need to do now is to take that and put it in the equation for the hydrogen ion concentration. Doing that, we get this value. So the acid is 1.3% ionized. So two things about the acid. It has a pH of 2.89 and it is 1.3% ionized. Ionization constants for weak acids. When weak acid dissolve in water, they undergo ionization to varying degrees. The degree to which each different acid ionizes in water is represented by what is called its ionization constant, Ka. See this subscript here is indicative of the equilibrium constant for acid. Ksp was for solubility product constant, Ke was for the equilibrium constant. So specifically now, because you're dealing with acid, its ionization constant is represented as Ka. The larger the value of Ka, the greater is the degree of ionization of the acid. Now we're given some Ka values for some acids here. Phenol is this, hydrocyanic acid, and so on. And you have citric acid at the bottom here. You can see that as you go downwards, the Ka value increases. That means that the degree of ionization of the acid increases downwards. So we can say, of all of these here, citric acid will ionize the most. The ionization constant expression, very similar to what we've done for the equilibrium constant expression. Only now you're doing it for an acid. And again, we'll use a very simple acid, ethanoic acid, to show how that is expressed. So this is the ionization equation. Its Ka will be equal to the product of the concentrations of these, as shown here, divided by the equilibrium concentration of the unionized acid. So this is the Ka expression for ethanoic acid. How do we go about calculating the ionization constants for weak acids? So what we'll do here, now that we are familiar with sample problem 2, we'll show how the ionization constant for that acid can be calculated. So repeat that problem again. If the pH of 0.100 mole per liter solution of ethanoic acid is found to be 2.89, calculate its ionization constant. So this is the ionization equation for ethanoic acid. You can see whatever concentration of it ionizes will give equal concentrations of these. Let's see what are provided. We're given the initial concentration and we're given the pH of it. This pH here can help us to determine the H, ion concentration. And since these two are the same, that will tell us what this one is. The only thing that is left to do will be to calculate what is left of that at equilibrium. We'll use the pH to calculate H plus. And we found what this was already. We know what the pH was in the previous problem. Go back to the previous problem. This problem had a pH of 2.9. And we found its hydrogen ion concentration to be this. Okay? So go back there now. Yes, that's the hydrogen ion concentration. Put it in decimal forms to get that. So we can now set up our IC table as you've done when we did equilibrium constant. That's the ionization equation. This is the initial concentration of the ethanoic acid. That initially we have 0 concentrations of these, but then we found that the hydrogen ions concentration is equal to this. That is what's going to be at equilibrium too. Well, because we are getting these, definitely the same concentration of the acid must have ionized to produce those. So we subtract that concentration from what the initial concentration was to give us the equilibrium concentration that turns out to be this. So we know all the final concentrations at equilibrium. We know what hydrogen is, we know what the ethanoic ions are, and we know what is the final concentration of the unionized acid. When you put all of that in the equation, the ionization constant for ethanoic acid is this. Let us suppose that if instead of pH, the percentage ionization was given to calculate Ka. In this case, we would have had to use the percentage ionization to calculate the hydrogen ion concentration. Using this formula here, you will know three things: the percentage ionization, the initial concentration of the acid, and of course, this 100%. Doing the math, the hydrogen ion concentration that is found will be the same as what you had before. So there are two ways in which this problem can be presented. Either they give you a concentration and a pH from which you can find the hydrogen ion concentration directly, or they could have given you a percentage ionization, and then you would have used this equation here to find H plus ions concentration, and then put those values into the Ka expression to give you that. We have a fourth sample problem, very similar to the ones you've done before, only in this case they're not giving you the initial concentration. They're giving a mass of an acid that was dissolved to make 100 milliliters of solution, having a pH of 2.6. And you want to use those values to find the ionization constant of the acid. So you know the pH. From that you can find H+. But we need to find the original concentration of the acid. We know that C is equal to N over V. We know V is given. That is V. When it's changed to liters, equal to that, 0.100 liter. We do not know what N is, but we know that N is equal to mass over molar mass. We know the mass is given. The mass is this. We do not know the molar mass, but we know the formula of the acid. See that? It has 7 moles of carbon, 6 moles of hydrogen, and 2 moles of oxygen. It turns out that that is a molar mass for the benzoic acid. So we know its molar mass, we know its mass, we can find its number of moles, we know its number of moles, divided by the volume, and now we get this initial concentration. It's just like if you're solving a normal problem. Now you're given its initial concentration and its pH. So do your ionization equation to show the stoichiometric coefficients by which the acid is ionizing to produce products. And its expression is this. Now we have to calculate the concentrations of these. We know how to do that. You're given the pH. Show you how to do that again here. Hydrogen ion concentration is equal to 10 raised to the exponent negative 2.6. It turns out to be that concentration of hydrogen ions. These two are the same. Set up our ICE table. That's the ionization equation there. These are the concentrations of these two ions. To find the equilibrium concentration of the acid, subtract either of these from its initial concentration. Yeah. In the end, this is the final concentration of the unionized benzoic acid molecules, and these are the concentrations of the ions that are produced. These are benzoate ions, and these are the H plus ions. Taking these and put them into the Ka expression, it turns out that this is what is a calculated value for the ionization constant for benzoic acid. I hope that was useful.